Okay, let's continue. There was one thing I forgot to tell about these notations. We may use this arrow notation OA and this small arrow in top part of this name of this vector, or this simple line there, single line there. But also there is, this is my formula book, and you can see that, where is my pen? I will show you. So many times in books they use this bold font for vectors. This sentence here is translated vektori A voidaan merkitä myös A. So this means vector A can be notated also by, here probably you can't see, but there is a small arrow there. But in this book, the notation is this bold font. In every formulas here, these letters which are written with bold font, they are vectors. I don't like this notation because you have to be very careful to see which are written in bold fonts and which not, because this means totally different thing. If you have a bold font, it is vector, and if you don't have, you have a what is that this usual font without bold, those mean they are scalars, they are simple numbers, those. And sometimes in some formulas it is very hard to understand if you can't be very sure if that notation means vector or if that means a simple number or scalar. And well, maybe it has been easier to write these books by using these bold fonts, but it is not so easy to understand. And when we are using or calculating with hand or with pen and paper, then this bold font is not useful at all, because it takes time to try to write that vector with bold font, and it is no use. So in written text we always use these lines or these arrows there. So let's go. One thing I forgot also. I every time forgot something. Here we had this vector notation, and here we have this line segment notation. This notation we may either think that this means the line segment or that it means the length of that line segment. And when we are calculating the length of vector, we may use some maybe 3 different ways to express or notate the length of the vector. The length of a vector. We may notate them with very many ways, and also we may call it with many names. We may call the length, or then we may use the word magnitude. This all means the same. Magnitude, or sometimes we may use absolute value, norm, and then what was that word one? Modulus. think these are the most common words, and these all means the same. In Finnish, length, it is pituus, magnitude, suuruus, absolute value, itseisarvo. Arvo means value. Itseisarvo. Itse means something like myself. Minä itse, myself. I don't know why. Itseisarvo. I don't understand the logic of this word in Finnish, but itseisarvo means the same as absolute value. This norm, we use it with the form normi. So again, the I ending there. This modulus is not so. I don't so often hear the word modulus there, but I've from the books I've found that kind of names for vector, the length or the magnitude of the vector. If I would change this to some kind of Finnish form, it would be moduli. But this is not so many. Actually, we don't use this word in case of vectors, but in many other cases, this modulus words is translated in Finnish with moduli, or sometimes with two U letters, moduli. Mostly myself, I use the length or magnitude. I think these two are the most common words I myself use. The length of the vector. The names, there are many names for a child you love, as it is said. But also the notations are there are probably, I think, 3 or 4 usual notations. For example, if we have vector OA as here, we may use the absolute value notation. The absolute value is notated with two vertical lines. So we may use the length of vector OA, the length of a vector OA, we may use notate it with this absolute value signs there, or this same way to express the absolute value for a number. For example, -7, the absolute value of a number -7 is 7, and we could notate it with these two vertical lines. Or then some used to this or I don't know if it is maybe it is for a reason that some people think that this absolute value gives a wrong feeling what that means, what that expression or notation means, and they try to solve the problem by using two vertical lines. So for example, this is a quite usual way to express the length of the vector. Actually, this notation is the norm notation. This norm is a concept which we use in vectors and also in matrices. And in matrices mostly it is used with these two vertical lines. But also you may use the notation that we are used to, for example, in geometry already. As I told, for example, if this picture, this OA would be a side of a triangle, we would notate it simply OA with no arrows or lines. Simple OA. So this is also possible. I think mostly I use this last version here, or then this first version if I want to somehow express that we are calculating with vectors. So I think during this course, I think mostly I have either of these notations. And the length of the vector is very easy. Actually, we are using Pythagorean theorem. So for example, in this case, this length here, it is very easy to understand that if we draw a triangle there, so it will be a right angle triangle, and with the help of Pythagorean theorem, we can calculate the length of this hypotenuse there. And of course, the same holds when we are calculating with vectors. We have this length here, we have 7 units, and this length here we have 3 units. And using the Pythagorean theorem, we can calculate the length of vector. So in this case, we can use Pythagorean, see this square root 7 squared plus 3 squared. And this will be the length of or magnitude of that vector. In this case, we did not have any dimensions here. We don't have any physical unit. But for example, if these numbers here would be, for example, meters, then the length of the vector would be also meters. If this is some kind of example of, for example, forces, then the unit may be, for example, Newton or kilonewton. Then these numbers will have units, kilonewton, and then the length or the magnitude of the vector will be also kilonewtons. And in this case, when we calculate this, what is this 749 plus 9? Is it 58? Square root of 58. And let's calculate the value of that so we can be sure that we get something useful. So this will be 7.6157, etc. And of course I could also measure it from this picture because I have these grids of 1 centimeter, so it will be about 7.6 centimeters. So I think we calculated that correctly. So this is a very simple way to solve the length of or the magnitude of a vector. And this same method holds when we have 3-dimensional vectors. For example, in 3-dimensional space, if we have example vector, let's take for example vector OB, and I will use this notation here. There are, for example, 2, 3, and 4 the coordinates of the point B 2, 3, 4 x, y, z coordinate and the length of this OB we can calculate with a very similar way. We just add the z component there. So we will have square root of 2 squared plus 3 squared plus 4 squared. For 13 plus 16, is it 29, I guess. Okay. We have used the notation where we have had these starting point and the end point of the vector OA. This is many times slow way to notate the vectors. We may also simplify that by using only single letters. In that case, many times we use a small case font. So when we have this starting point and ending point of that vector, we mostly use this uppercase letters there, big O and big A. But if you and then we use this OA notation there. But if we want to simplify that so that we will name the vector with only one letter, for example A or B or C or whatever, for example V, then we mostly use the lowercase font there. Let's take this kind of vector V. So I will use only one letter, and this is small case V letter, V in Finnish. And now I will use another notation to get used those. I will use this kind of notation where I will use these unit vectors there, I, J, and I will get a vector 5i minus 2j. And now I want to calculate the unit vector which has the direction of v. Let's find out that unit vector which has the same direction as vector v. What does that mean? I will draw. Mostly we don't have to draw when we are calculating with vectors. We mostly do not need to draw an exact picture. For example, here I took my time to get some kind of good picture of this vector OA, so that we could see where that is located. But mostly it is enough to draw some kind of approximate picture of that vector. So these drawings do not take so much time. mostly when we are solving problems with concerns vectors. But at this moment I will still draw the picture, and I will draw the picture right now so that I get 5 units. The vector goes 5 units to the right, and this is -2. +2 would mean that it goes to the direction of positive y-axis, but now when it is minus, it means that the direction is to the direction is the direction of negative y-axis. So let's draw that picture there. Now we need only draw a small part. Here is positive y-axis and positive x-axis there, and the point which is the end point of this vector v is 5 minus 2, so it is in my coordinate here. We have here 5, and here we have -2, and the vector will be this vector here. This is origin there, O. And this unit vector, which we are trying to find out now, means that it has the same direction as this. This is called v, this vector. It has the same direction as this. I don't like my picture. Let's draw a little bit bigger. It has the same direction as this vector here, but it has length of 1 unit. So that means that when I have this grid paper here, which I have 1 square is the side of the one square in this grid paper is 1 centimeter. So in this case, this 1 unit means the 1 centimeter in my picture. So that means that we have to find out that vector which has length of 1 unit. So it starts from the origin there and ends up to the point where the length is 1 unit. And now we have to find out what is the formula or what is the vector expression for this unit vector. And at this moment we only have to practice how to solve that unit vector. But this is mostly used when this method is mostly used when we are calculating with 3-dimensional vectors. For example, we are calculating with forces which act in three-dimensional space. For example, these pens means that the forces which are attacked to my thumb at this moment, and these forces are orientated in, for example, these directions, which you can see here probably. And now we have to calculate, for example, the sum of these forces. And in that calculation, we may need, it depends on the case, we may need those unit vectors. Or then we may have the problem that we know that this force system here in this 3-dimensional space is in equilibrium. So that means that these forces cancel each other, so that the sum force is 0, or we may call that resultant force. Sum of forces, it's called resultant. We know that this is in equilibrium, so these forces cancel out, and in that solving process we need those, or these unit vectors are very useful. It helps us a lot. But in this case we don't necessarily yet need that unit vector anywhere, but we are just learning how to calculate the unit vector. So first calculate the length of V. Length, or again we may use all these concepts there. Length or magnitude, absolute value or norm or modulus, these all mean the same. But this is the first step. So let's calculate that. V, and now I will use this absolute value method there. And we have the vector notation here. The components of those vectors, unit vectors, the factors in these unit vectors, there are 5 and -2. And with the help of Pythagorean theorem, we may calculate the length of this vector by using squaring 5 squared plus -2 squared. Here we have to use the brackets because we have this negative number there, and it has to be squared, so we need those brackets there. And let's calculate the length of this 25 -2 squared. It is the same as 2 squared, so it is 4. So the length of this vector is 29. I don't suggest to use any decimal values in this point. It will be helpful if we only use this square root notation there. Somehow I got the same length of this vector. It was just a coincidence there. And this is the length of this vector. When we divide that length by itself, if we divide this number by square root of 29, we get 1 unit. And the same holds when we are dividing the vector V with or by this length of the vector V. We will get the unit vector, which has the same direction of this as this vector, but it has only the length of 1 unit. So next, divide the vector V with the length of it. So that means we will divide this V vector by the length of V vector. So as you see, the notation is very important. It is different thing to have V and this absolute value of V. The absolute value means the length of that vector or the magnitude of that vector, but without those absolute value signs there, then it is only simple vector there. So I will give a notation for this very soon, but let's calculate this first. So we will divide 5y minus 2j by square root of 29. Well, this is exactly the same as if we had a simple algebraic expression here. Now we have vector in the top part of this division here, but we can use the same calculation rules as we would if we have a simple algebraic expression in the top part of this division here. And what does that mean? That means that we may divide this first part there, so 5y, we may divide it by 29, square root of 29, and also do the same with this 2j part there. Many times right now I am I'm writing all the intermediate steps there, but many times when we are solving or trying to find out the unit vector, we skip those intermediate steps because it is very easy to see how do you get that final answer. So in this case we have we may express this as this way. And if we now do the division there, so if we divide this 5 by square root of 29 and 2 by square root of 29, we will get, I will write the decimal expression now. Wait a minute, I will get it very soon. 0.2, 92847.6. This is the factor of I, unit vector I, and then we have this another here, 2 divided by square root of 29, we will get as soon as my calculator works. What is the problem? Yeah. So in this case, the unit vector will be such that it starts from the origin of the coordinate system, and it goes a little bit. Sorry, let's round this. It goes about approximately 0.9 units to the right and approximately 0.4 units down. So if we are checking here, if we have this 1 unit, the length of 1 unit of this vector, we will have be at this point here. I will draw that with a different color. This is not probably good color. Maybe this. I will draw this unit vector here. So it is not, if you watch carefully or very, you may see that it is not 1 unit to the right. It is a little bit smaller. From this picture, I would guess it would be 0.9, as we see from this answer here. And how much do we go downwards from this x-axis? From this figure, we may guess or approximate that it may be maybe 1/3 units. So we may approximate it would be about 0. For example, 33 from this very bad drawing. And now we see that we calculated it will be 0.37. So my drawing is quite near from the answer I got from this calculation process. This unit vector here, we may say that, for example, with a simple coordinate system, as in this picture here, I draw this picture, and I chose the unit to be one grid of this paper, or one side of the small squares of this my paper, which had squares of 1 centimeter size. But that is important. I have to choose what is the unit of this coordinate system, because if I don't know what is the unit, I can't draw. I am not possible to draw anything in that coordinate system. When I know that this point means 1 unit, then I can find the 5 units here, because it's 5 times that 1 unit there. And also this y coordinate here, this is -2. I need to know what is 1 unit. So 1 unit is, or actually this here, 1 unit upwards is unit vector j, or the positive unit vector in the direction of y coordinate axis. I have to know the unit so that I can find the place of 2 or -2. The same holds with the unit vector. When I have vector v, in this case I knew the vector expression, but this unit vector means exactly the same as the number 1 in this our coordinate system. 1 unit vector in the direction of vector v is this blue vector there, and we got the length of the vector v. It was 29 units. We had the same calculations here. The length of the vector v is 5.38 units, and if we take this vector and we add 5.38 unit vectors, we will end up to get the v vector, or vector v. The length of this vector is this, as we calculate this. This was just a coincidence. We had the same value there in the different example, but the length of this vector is 5.38, 5.4 from the figure we may guess. So 5.38 unit vectors gives us the vector v. This is very simple thing, and it may sound stupid to concentrate so much on this very simple example, but this is very important thing in the future when we are calculating with the 3-dimensional vectors. With 2-dimensional vectors, or in 2-dimensional case, we many times we don't get any use for vectors. We can solve these problems many times without vectors, but it is easy to understand the behavior of these vectors and the elements of the vector calculators with the help of 2-dimensional examples. Because when we are moving to 3-dimensional space, we can't anymore draw pictures, or of course we can try to draw, but it is very hard to see anything from that picture, and at least it is impossible to measure anything from that picture which we are drawing in a paper. Or of course we could use also some computer programs to draw those pictures, but we can't measure anything from that picture when we are using three-dimensional space. And then the only way is to use these same methods as we learn in the beginning of this course, by using only these plane vectors or two-dimensional vectors. Okay. I had something to say, but did I already? Let's take another example, or those calculation rules which we need. Some calculation rules for vectors. As addition and subtraction. These are very, very easy rules, and I think most of us, if we had not taught how to add vectors or subtract vectors with vectors, I think we could invent the same rules. Those are very, very easy to understand. For example, if we have vector A, which is, I will use this bracket notation. For example, we have vector A, which has components 1, 6, and then another vector which is called B vector, and it has components -3 and let's take 2. And when we have to add those vectors, we just add them. So when we add these vectors A plus B, we get the sum of these vectors. I many times use these brackets in vector calculations because they are so much quicker than using these I and J unit vectors there. It is much easier to use this method. So the rules is very simple. We just add the x components and the y components. So with those first components there, we have 1 and -3, so 1 plus -3. This is the first component, and then 6 plus 2. So we add two second components there. So this is very easy rule. 1 plus -3, or same as 1 minus 3. It is -2, and here we get 8. So when we add these vectors together, we get the vector -2, 8. Let's check that by drawing. I will draw a picture. Again, I will point that mostly during vector calculations we don't need any pictures or graphs from the problem. But in this the beginning of this course, it is many times useful to draw a pictures to see the rules, how these rules are they how do you say, are they reasonable? Do you accept those rules? And when you are using pictures, you may many times understand that rules is okay. These rules are okay. And now I will draw these vectors. Just me a little bit thinking. I will just have the space there enough to get the pictures correctly. So y and x axis here. And right now I will draw first the vector A, which has components 1 and 6. So it starts from the origin and it ends to this point, 1, 6. So x coordinate is 1 and y coordinate is 6. So it will end here. So here we will have 1 and here we will have 6. So the A vector or vector A is this vector. This is A. Sorry for my picture. I hope you if you made some notes there, you made a better choice. But right now my picture is so that I can draw this picture, this vector B there, but I was stupid when choosing the place of this origin. Well, sometimes this happens, because now I have to find out the place -3, 2, or the point -3, 2, and it is exactly here. So this is the I looked not so carefully that. So this is vector B. And what does the addition of those vectors mean? In graphic meaning, it means that we are adding those vectors together, so that if we have first vector here and another vector here, let's take the same colors as here, we have these vectors here, and we want to add these vectors together. We just move the other vector to the end of the first vector. So for example, if we are using this vector, we are drawing this vector first, and we are having this B vector here, so we add this B vector to the end of this A vector, like this. We have the length and the direction the same as we had here in origin. We have here those vectors, and we are moving it with the same direction to the end of this A vector. And from this picture we can see that if we have this A vector here, and then we are moving from this point -3 in the horizontal direction and 2 in the vertical direction, where do we end? We are moving 3 units to the left, because it is -3, and then 2 units upwards. So -3 and 2, we will end up there. So I will use this kind of line here. So this is the B vector here. And where did we end? We started from origin, then we move along the A vector here, and then we moved along the B vector here. And what are the coordinates of this point? We can see that it is 2 units left from y-axis. That means the y-coordinate equals x-coordinate equals -2 because it is 2 units left, and then we move from the x-axis upwards 1, 2, 3, 4, 5, 6, 7, 8 units, and we end up to this point. So that means that when we are adding these vectors together or in line there, so when we move along the A and then move along the B, then we will end up to the point which is the same point, that is the end of the vector A plus B. So this sum vector here is, I will use this color. Sorry about my picture. I didn't see the where did it end. So this vector is equals A plus B. But as I told, this picture method here, this is easy method to understand the rules of the sum or addition rule of the vectors. It is very easy to understand that it is okay. It gives reasonable results, but this is very slow method to solve these problems. And as you see, we get the same result without any pictures. I didn't draw this picture to get this answer here. And this is a good thing because when we are using three-dimensional vectors, we are not able to draw any exact pictures, and we can't from the pictures see almost anything. It is almost unnecessary, or it is not useful to draw any exact pictures with when we are using three-dimensional vectors. But we see that we get reasonable results, and this rule is very easy to understand. And the same holds with I'm not going to draw any picture with this, but let's take another picture, another example. If we are having, for example, vector C equals, I will take a three-dimensional vector right now. I will have 5, 2, 10, and then I will have D vector -1, 3, 7, and let's take a third vector E, and let's take that 0, 0, and 4. And now we need to calculate sum and now we have to add and subtract these vectors. So for example, if we have to calculate what is C minus D plus E, this is our problem. What do we get when we get the vector C and then we subtract D from that and plus or add the vector E? So how do we calculate? We calculate it by writing these components here. We have here C vector, then we minus D vector and add E vector. So in this case, I lost space. I should have written that a little bit higher than in the paper. I need another paper. So I will continue it here. This is almost the same as in algebra. We had these rules when we had to take away brackets, and we had the rule that when you had a plus sign in front of a bracket, not you just could take away those brackets. But if you had minus sign in front of brackets, you had to change all the signs inside those brackets. And here with vectors we have the same rule. So for example, and again you don't need to solve this so with so many intermediate steps, but in this point I will draw something to see to show how do we get the solution. So first we have this first vector, we don't do anything there, and then we have this minus sign there that will change the signs of these components inside of these brackets here. So I will change the plus sign, and then I will change all these signs. So I will get 1, minus 3, minus 7. Note sign changes because of that minus sign there. And then we have this last vector here. We will add that right now. And now we have only these plus signs there between those vectors. So after that we will get, we may add them by components. So first components we add together, then second components we add together, and then third components we add together. So we will get 5 plus 1 plus 0, 2 plus minus 3 plus 0. Of course you may also write this as with the 1 minus sign. And then we have 10 plus minus 7 plus 4. So here are first components, and here are second components, and here are third components. Then we just add 6 and minus 1 and I guess 7. So as you see, this was a problem in three-dimensional space, and we had no need to draw any pictures. This may have meant that we have a problem with mechanics or statics, where we have three forces: first force, second force, and third force there. And these components tells us what size of that force goes along the x-axis, and what size or what part of that force goes along the y-axis, and what part goes along the z-axis. And then we have to add those sums together, those forces together, and get the final force. What is the sum force of those three forces? Many times we call that resultant. The sum of vectors is called resultant. And this will be the resultant. It would be, for example, that the sum force of this example is 6 kilonewtons to the direction of x-axis, minus 1 kilonewton to the direction of y-axis and 7 kilonewtons to the direction of z-axis. And this we could solve without any need to draw any pictures. And I'm not even trying to draw any pictures of this because it is in three-dimensional space. It is very slow and very hard to draw any exact pictures, and finally after you have made used so your time to draw that picture, then finally you notice that you can't find out anything from that picture. So that's why I'm not even trying to draw that picture there. Okay. Yes, I think this 1632. I think today we will end at this point. Next time I will continue this vector calculations. There are some exercises there in the Moodle. I picked them from one book which I don't find right now, but it is the same book as I had the link in here here this book. This is not the same edition. I'm not sure if I probably have an older edition, but I will add that link also to the Moodle page. But that link is in the algebra and geometry Moodle page. There I probably gave an I don't remember. Maybe it was cosine rule and sine rule in geometry or triangles, and there was some exercises, and probably in that case I gave you that link that you may practice or train your triangle sine and cosine rules in triangles with the help of that online book. And this is the same book. I have scanned these problems there to the Moodle, so you may practice with these, and if you find something to ask, just you are free to send me messages. But I think today we will end to this point. I will add these videos to the Moodle when I get when YouTube gets that ready, and the next time we will meet, I think it is Friday. Then we will have only two hours lessons. But right now, I hope you have started your studies in this January. I think maybe you have had today the first lessons in every courses, and I hope you will have enjoyable time in your studies this spring also. But let's have a break from mathematics at this point, and let's continue at Friday. I will add those assignments to Moodle as soon as I get something done. But probably the first assignments I will give next week, not yet, because the campus group will start their studies next week. So I will not be in hurry to give those assignments before they have had any lessons at all. So you have to wait, and of course I have to wait also, because I have not done any assignments yet. But they will be there in the Moodle as soon as possible. Okay, let's end these lessons right now. Bye bye.